So greetings to all the audience. It's morning in Texas, so I would say good morning to everybody. The talk that I will be presenting today is on strongly correlated system and two of the properties that strongly correlated system manifest. One is Polaron formation, another is metal-insulator or insulator-metal transition. Before I forget, I would like to thank the organizers for giving me the opportunity to present the research from my group. Again, so that I don't have to do it in the last slide, the funding acknowledgement is from NSF, Department of Energy, and a National Renewable Energy Lab, which is a national lab under Department of Energy. Now, the most of the computational work that I will be showing today is done by my student Horipada Sarkar, who recently graduated, and these are the list of my collaborators, experimental collaborators, I would say, who contributed in our work in different stages and different times. The computational work were done in Texas Advanced Computing Center. A brief outline of my presentation today. After providing introduction, we will go to the Polaron formation, especially a case study on Polaron formation in bismuth vanadate. Then we'll go for the metal-insulated transition in rare earth chalcogenides, again a case study, and would like to draw some general conclusion. When we talk about climate change, it's kind of give an impression that, yeah, it's happening, but the impact of it may be felt in future. In a recent article in New York Times, I note the date here, it showed, or it basically discussed from some publications that more than a third of heat deaths are basically related to climate change. To demonstrate this fact, why? As you can see, this is a plot of average annual temperature of our planet Earth. As you can see, until recently, the temperature was fluctuating, but it was not increasing much. Then something happens. Of course, we know what happens. We are using lots of energy from fossil fuel, and the average temperature is basically increasing now, almost exponential. This is a projection up to 250. And as you can see, the projection looks not very good. Average temperature is increasing by more than 2 degrees Celsius. But of course, there are mechanisms, or we should do something to curb this increase so that it remains at least in this average fluctuation level. And this is one of the main motivation of the work in my group, harvesting solar energy for renewable and sustainable energy. One of the very known technique or technology to do that is photovoltaic, where light are absorbed, electron-hole pair are created in this PN junction type structure, and those electron and hole then can be conducted via the external circuit, and then this photovoltaic or current can be used to do other works. Driving our electronics or any other thing. One of the way this is now used is that using that photovoltaic to drive electrolysis of water, splitting water into oxygen and hydrogen. And what it needs is, we call photocatalyst, anodic or cathodic photocatalyst. These are usually semiconductor. This PV electrolysis is nowadays becoming very popular. Our work, or for the presentation today, will focus on these photocatalysts. These are usually semiconductor, and in this reactive condition, in liquid solution, it could be water with some pH values. Sometimes it's highly corrosive reaction environment. We have found from experience of several decades that metal oxides or metal chalcogenides may survive this kind of environment, reactive environments. That means they're most likely to be more stable. And hence, the whole talk today will be based on metal oxide and later metal chalcogenides with electronic contribution that creates a strongly correlated system. A very simple cartoonistic view how those photocatalysts work. These are semiconductor, hence we'll have valence band and conduction band with a band gap. Once light is shined, light get absorbed, electron-hole pair is created. If we have an interface with some liquid solution, let's say water, that will have some two chemical potential. One is for oxygen evolution reduction potential, another for hydrogen. If this oxygen evolution reduction potential is higher than the valence band age, valence band maxima, then hole can go through and drive this oxygen evolution reaction. Similarly, if the conduction band is higher than the hydrogen reduction potential, then electron can also come down and can drive this hydrogen evolution reaction. In general, this is a schematic diagram to show the necessary properties or the properties that needs to be optimized for this semiconductor to be an efficient photocatalyst. Basically, three key requirements. One, appropriate band gaps. The water splitting potential is about 1.23 volts. Hence, the band gap has to be greater than 1.23 electron volt. Second property that is important, once the electron-hole pair is created, this pair can be called exciton. This exciton should be broken easily. That means electron and hole, they should get separated easily. And the third, once they are separated, the conduction of those charge carriers via the bulk up to the interface, that conduction within the semiconductor has to be good enough. So the third property is charge transport. In our group, we work on all these three properties to modify the photocatalyst or even to discover new photocatalysts from our theoretical algorithm. But for today's talk, we will discuss two properties, as the title indicates, which relate with the third one, the charge transporter, which impact the charge transport. The first one, we will talk about Polaron formation in metal oxides. I'd like to thank the previous speaker for introducing Polaron in his talks. I will not go very detailed, a brief discussion or brief introduction of Polaron for the purpose of my presentation. So what is Polaron? Polaron is basically, if there is an extra electron, it can be from electron excitation or an electron from, let's say, doping or anywhere else. If there is an electron moving through the lattice, and if the electron motion is slow enough so that it can create lattice distortions, the lattice can be distorted enough to create a potential well so that the electron can get trapped. So this lattice distortion plus electron or hole together create Polaron. It is a kind of a quasi-particle. We can categorize Polaron into two different classes by some obvious intuitive definition. One is a small Polaron. We call it a small Polaron when the size of the Polaron wave function or the extent of the Polaron formation is smaller than unit cell, or we can say the lattice distortion is less than the lattice parameter of a unit cell, or a large Polaron, as exactly as the name suggests, if the extent of the Polaron is much larger than the unit cell lattice parameter. Now, the Polaron, as the previous speaker mentioned, it does impact the photoconduction or conduction in the materials. A quick view of that. If we consider silicon, the diffusion length could be at the micro, in fact, it's a bit higher than micro, it's 100 to 200, sometimes even more than 200 micrometer level. Once we come for the bismuth or iron oxide, these both have 3D electron. Bismuth, vanadium has 3D, iron has 3D. Then as you can see, the diffusion length order drops significantly, more than 4 order of magnitude. So this is what happens when Polaron formed in materials. the transport is deteriorated. Now, computational methodology, what we did, we used density functional theory. As density functional theory by itself, with their standard approximations, we know that they underestimate electron localization or electronic correlation. Hence, we use DFT plus U, where U is a Hubbard electron correlation parameters. We sometimes, it's a tradition to say parameters, but nowadays we can calculate them from first principle method as well. Then the way we model Polaron is that if we have a unit cell, we can pick up a site on which the Polaron can be formed and add electron or hole, depending what Polaron we want to model, and then add a small perturbation on that site to ensure that electron or hole, at least initially, reside on that site. Then we do complete full relaxation. Even after the relaxation, if the electron with density or the charge density is still found to be localized on that site, if it is an electron, then it's electron Polaron, or if it is a hole, then it's hole Polaron. All the calculations for this presentation were done with the FASP ab initio code. So we'll start with bismuth vanadate, a case study for Polaron. We have published paper on other materials as well, but today I will talk about bismuth vanadate. It is one of the very popular anodic photocatalysts that there are plenty of publications in literature. So this is just initial checking of the lattice parameter with our work versus experimental and other calculation. We see very good agreements. It's just starting check. And then I would like to present the electronic structure of pristine bismuth vanadate. 2 points to note here. One, the band gap. The calculated band gap is 2.10 electron volt, whereas the experimental gap is between 2.4 to 2.50 electron volt. So there is an underestimation of the band gap, which is typical for density functional theory band gap. The second point I would like to note for Polaron formation, we know that whole Polaron usually formed near the valence band, and the valence band of bismuth vanadate is dominated by oxygen p orbital. So Polaron likely will form on oxygen side, the whole Polaron. Similarly, electron Polaron will likely to be formed on the vanadium side because that conduction band minima is dominated or is mostly from vanadium 3d orbital. This slide I will go very quickly. Just to show another property that if we calculate the electron effective mass for pristine bismuth vanadate, it is 2 times than the bare electronic mass. Initially, we tried to lower the effective mass by doping with more delocalized dopant like niobium. The effective mass goes down. However, it is still more than 1.5 times of bare electronic mass. The key question here, now these are experimental figures, just a typical experimental figures that indicate the Polaron formation below the conduction band. So the main question we are going to ask here, that what type of Polaron forms in bismuth vanadate? Because we know from experiments, Polaron forms in bismuth vanadate, but we want to make sure that we understand what type of Polaron, which is more dominant, and how they affect the transport. We form electron Polaron on the vanadium side, the way we described it 2-3 slides ago. The first thing, again, that electron Polaron localized at a vanadium site, and this is how the charge density look like, a magnified view. And definitely because of a charge trapping, electron trapping, the charge state of the vanadium atom changes, and these are the corresponding lattice distortions around that vanadium atom. Both of these two are kind of, we can see the footprint of Polaron formation. And the third footprint, if we want to look, is at the electronic level. With compared to the pristine bismuth vanadate density of states, we see that electron Polaron formed about 0.4 electron volt above the conduction band minima. And this is mostly formed by vanadium 3D orbital. This is the amplified view of this peak. This green line as the same color scheme we used for the pristine and the doped one. The green line is the green DOS is the vanadium 3D orbital, and it shows the charge density, a feature of d orbital. Then we do the whole polaron on the oxygen side. Again, the whole polaron localized at the oxygen side. It shows kind of a feature of p orbital, oxygen p. It is formed at one side and also the corresponding lattice distortion. And then electronic feature shows that the whole Polaron state form at about 0.8 electron volt above the valence band maximum. Another point I would like to mention is that for both of the electron and hole Polaron that we have seen, the distortion they create is very local to the site. Hence, these are small Polarons that is created within bismuth vanadate. Now, a summary of this Polaronic result and compared with experimental results from our collaborator is that if we consider the band gap, again, the band gap is smaller in our computations. However, if we consider the Polaron state formation, electron Polaron and hole Polaron, the energy values, those are created below the conduction band, 0.4 versus 0.3 electron volt, whole Polaron formation, 0.8 electron volt versus 1.02 electron volt, they do compare well between our theory and experiment. Another question I think that needs to be asked is that what is the practical consequence of forming this Polaronic state within the band gap? One of the consequences can be that the reduction in photovoltage. That means if Polaron didn't form, the photovoltage could have a higher bound of the fundamental gap. But now because of the formation of this state within the gap, the overall reduction in photovoltage takes place. And that has been verified by the experiment from our collaborator at Darmstadt in Germany. Now, a quick view of how Polaron transport happens. It's basically hopping state to state. So if this is an electron Polaron, it will hop from one vanadium site to another vanadium site. If it happens, it has to go through this energy barrier. We call it activation barrier. We calculated activation barrier for both electron and hole. Hole activation barrier, about 0.3 electron volt, is lower than the electron activation barrier, which is about 0.4 electron volt. So from these numbers, we can see that hole can move with a higher probability than electrons. Then we get some numbers for the Polaron mobilities for both of them. For that, we use an equation which is called Einstein equation for transport. E is the electronic charge, 1 minus C is the hopping probability, A is the hopping distance. The quantity that we need to calculate now is this nu zero, which is the phonon frequency of the site, of the Polaron site, if it is anion or cation. To do that, we calculated phonon dispersion plot and phonon density of states. From there, we get the typical phonon densities of vanadium and oxygen. With that, we calculated the Polaron mobility. Again, it shows like the activation barrier. Whole Polaron mobility is higher, at least 3 times higher than the electron Polaron mobility. Now, if we compare these mobilities with silicon, for example, it clearly shows that the mobility in bismuth vanadate, either of this electron or hole Polaron, is 9 order of magnitude smaller than the mobility in silicon. That shows that Polaron formation severely limits the electron or hole transport. Now, a question can be asked, can we improve this Polaron-related conduction problem? Can we suppress Polaron? One of the way it can be done and has been proposed as well is by doping or alloying or making solid solution. Of course, we need to choose those dopant carefully. Now, if we do that thing, then we may encounter another phenomenon. That's where we go to the second part. The metal insulator transition that can happen, or insulated to metal transition that can happen. Now, if it goes from insulated to metal, of course, this would be beneficial. We don't want a metal, of course, because then metallic behavior means we will not get any photovoltaics. We need a semiconductor. Hence, if this phenomena happens, that also affect the performance of these materials. The resistivity of these materials when this metal insulator transition takes place, they changes either with respect to some thermodynamic variables like temperature, pressure, or electronic chemical potential. So electronic chemical potential can be changed by that doping or making solid solution. So this is what we will be describing in next few minutes. This work started with calcium lanthanum sulfide. And when cerium is incorporated in calcium lanthanum sulfide, as the cerium concentration increases, we see the color of the sample, they are changing. It's getting from gray, it's not exactly gray, it's like whitish, it's not a metallic color, to a red color. And red color we know is band gap less than 2 electron volt, would be good for catalytic materials. So the initial goal was to understand the color change and to see what kind of transport is taking place in these materials. This is how we started this work. With no cerium, calcium lanthanum sulfide, there is no occupied 4f electron compared to this solid solution. Cerium, the last end, x equals to 1, calcium cerium sulfide has the highest density of occupied 4f electron. And we know that 4f electrons are highly localized electron. That means a strongly correlated system. The crystal structure of these materials, of this solid solution, is the parent structure is thorium phosphide structure. So thorium phosphide structure remains same whether it become lanthanum sulfide or cerium sulfide, or when we start in mixing them with varying concentration of cerium. The structure remains same, and this has been verified by our collaborator at UTA from neutron diffraction measurement. We know that the structure remains same. So when we calculate it, we take the same structure like lanthanum cerium sulfide. The question is why calcium is in there. One of the reasons why calcium is in there is that if we have calcium, or it's an experimental result, then the synthesis temperature for the lanthanum sulfide or cerium sulfide becomes lower. That makes them easy to synthesize. Now that's an experimental result, and our recent publication also shows why calcium does it. Another point to be noted that without calcium, lanthanum sulfide, these lanthanum have spin magnetic moments, and there are 12 lanthanum atoms, and they can be organized in 3 different groups. Similarly for cerium, when we put calcium in there, we choose one of these group to replace lanthanum by calcium, and we have found that configuration is more favorable than random distribution of calcium within the structure. Similarly, when we start putting cerium in calcium lanthanum sulfide, we started to substitute cerium by taking group by group. And again, we've calculated stability, both the site selection method versus random distribution. This site selection method seems to give better or more stable structures. Also, we check the magnetic state when there are no cerium atom. X equals to 0, this is non-magnetic. As soon as ceriums are incorporated, the cerium atoms within the structure started showing anti-ferromagnetic behavior. Then we start calculating the electronic properties. We will start with the calcium lanthanum sulfide when X equals to 0. A DFT only band structure shows band gap of 2.06 electron volt, where the unoccupied 4f electron shows just above 3 electron volt. And this mix are basically those lanthanum 5d orbitals and some of the sulfur p orbitals. Now we add U value on lanthanum 5d orbital. What it does, it pushes these bands above, as you can see, but we couldn't add U value on the lanthanum 4f orbitals because those are unoccupied. U method, DFT plus U method doesn't work on unoccupied electrons, hence they remains almost at the similar position. What it does, it gets decoupled. Within this formalism, it shows like a charge transfer type Mott insulator. Even though this has limitations, as I just mentioned, for DFT plus U, but this overall feature seems to be correct according to experimental mobility measurement. Now, these are the band structure for all of them from x equals to 0 to x equals to 1. Again, as we mentioned, that this band gap is highly underestimated based on the color of the sample. This kind of whitish sample color should be, the band gap or optical gap should be above 3 electron volt. We get highly underestimated gap. On the other hand, when cerium start coming in there, we compared the gap with the trend of the optical gap or absorption measurement. The trend is maintained. So this one is for calcium lanthanum sulfide. As you can see, that optical absorption is started somewhere around 3 electron volt. Another thing that I would like to point quickly is the bands near the conduction band or near the Fermi level with higher cerium concentration. We see that there are some partially occupied or fully occupied bands around this conduction band continuum. We'll look at this closely in the next slide. What happens as we start increasing the cerium or 4f electrons concentration at the higher value of x, there are fully occupied bands. The red bands, this is a portion of the bottom of the conduction band. These red bands are fully occupied, green bands are partially occupied, and then the black bands are unoccupied. What we see with x equals to 0.75 and x equals to 1, that a fully occupied, partially occupied to unoccupied, this create a continuum without any gap in these two. Hence, they show metal-like behavior. It is a counterintuitive in a sense that we are adding more localized electron, and it shows more like a metal behavior with higher 4f electron concentration. Now, we also compared this with the measurement of photocurrent density, because this was a collaborative work between one of our UTA colleague in our department, in our university. The current measurement shows if it is calcium lanthanum sulfide, as we have seen, it gives almost like charge transfer type Mott insulating behavior. It gives a current of microampere level. On the other hand, the ones which has higher cerium concentration, they give current around at the milliampere level. So with higher cerium concentration, there is a 3 order of magnitude current density increases. However, for photocatalyst purpose, I would say that this milliampere level current is not sufficient enough to drive the water splitting reaction efficiently. However, it does show some increment of current. So in conclusion, this is kind of a general conclusion that we know that for a strongly correlated system, it shows many exotic phenomena. We basically studied or presented 2 properties, that 2 phenomena that are relevant to photocatalyst. One is the Polaron formation, another is insulated to metal transition. We try to argue that effective band gap can be reduced by Polaronic gap, in addition to slower electron mobility or hole mobility, which restrict the photoelectrode's optical gap. Doping and alloying may improve Polaron conduction in terms of by suppressing the Polaron or adding some delocalized hybridization with the Polaron states. However, they may initiate some kind of electronic transitions, such as insulated to metal transition, we have shown here in this particular presentation that when you formed a solid solution by adding cerium on calcium lanthanum sulfide, we see that from x equals to 0 to x equals to 1, a transition goes from MOT or charge transfer type MOT insulation to almost like metal type of behavior or metal type of electronic signature in calcium cerium sulfide. The calcium lanthanum sulfide with no 4f electron was non-magnetic. However, the others are AFM. The optical transition, that was the initial goal of the work, which I didn't show here because it's not exactly the goes with the title of this presentation, that we have found those orange and red color comes due to intra-band transition from cerium 4f to cerium 5d electronic excitation. And finally, even though DFT plus T method kind of model the system and give some overall information which matches with experiment, but we did find that for the detailed numbers, this method, or for unoccupied 4f electrons or 3d electrons, this method has some limitations. We work on some improvement of this method and other method as well. So that is basically my talk. Thank you very much for your attention. And finally, these are my group members. This is a photograph of a group lunch just before COVID.